Welcome to our lesson on alternating current. Today we are going to explore the type of electricity that powers most of the equipment you will encounter in the field, from air conditioners to heating units. We will cover what AC is, how it is generated, and how to read its waveform. Before we dive into alternating current, let us quickly review direct current, or DC. In a DC circuit, the electrical potential remains steady. Because of this, the current flows in only one direction, constantly moving from the negative terminal of the power source through the load and back to the positive terminal. Alternating current behaves quite differently. Instead of a steady one-way street, AC current flows in both directions. It moves in one direction for a moment, and then the power source reverses its polarity, causing the current to flow in the exact opposite direction. This constant back and forth is the hallmark of AC power. You might wonder why we use AC instead of DC for most things. In fact, about 90% of all electric power consumed globally is AC. This is primarily because it is incredibly versatile and much cheaper for power companies to produce and distribute over long distances. By using transformers, AC voltage can be easily stepped up for efficient, low-current transmission, which minimizes power loss, and then stepped down for safe use in homes. So where does this alternating current come from? It comes from AC power sources, commonly known as AC generators or alternators. These machines create voltage by using the rotary movement of a conductor, like a wire coil, inside a magnetic field. Whether the coil is turned by flowing water, a wind turbine, or steam, this mechanical rotation is what generates the electrical power. Let us look closer at how that generator actually works. As the wire loop rotates, it crosses the invisible lines of magnetic force between the magnets. This magnetic field applies a physical force to the free electrons inside the wire, compelling them to move. This movement of electrons creates an electromotive force, or voltage, which is then transferred to an external circuit using slip rings and brushes. To understand how this reversing voltage behaves over time, we use a graphical representation called a waveform. On this graph, the horizontal line represents time, and the vertical axis represents the magnitude of the voltage. When the wavy line is above the zero mark, the current is flowing in the positive direction. When it dips below zero, the current has reversed into the negative direction. Instead of just measuring time, we can also label the horizontal axis in degrees of rotation. This perfectly maps the output voltage to the physical position of the spinning generator coil. A full circle is 360 degrees, which corresponds to one complete revolution of the generator armature, and therefore one complete cycle of the alternating current. This specific smooth curve produced by a simple AC generator is called a sine wave. Notice how symmetrical it is. The voltage is exactly zero at 0, 180, and 360 degrees. The maximum voltage occurs at 90 degrees in the positive direction and at 270 degrees in the negative direction. When working with multiple AC circuits, we often talk about phase differences. We use the degrees of the cycle to compare them. If two circuits hit their peaks and zero points at the exact same time, passing through 90 and 180 degrees together, they are perfectly in phase. If they do not match up, they are out of phase. Finally, let us discuss frequency. Frequency is the speed at which these cycles occur. Standard AC power in North America has a frequency of 60 cycles per second. We measure this in a unit called hertz. So 60 hertz means the generator is spinning 60 times every single second, producing 60 complete sine waves. In each of those cycles, the current changes direction twice. To wrap up, alternating current is a highly efficient form of electricity that constantly reverses direction. It is produced by generators that spin wire coils through magnetic fields, and we can visualize this power using a symmetrical sine wave. Understanding these fundamentals is crucial for troubleshooting any modern electrical equipment.